Good evening to all present over here in the physical mode as well as in the online mode. I welcome you all in this tech talk. Uh, this tech talk is basically organized by ACM Student Chapter IIT Jodhpur. So let me just give you a brief about ACM Student Chapter. ACM Student Chapter IIT Jodhpur is a research community of undergraduate, postgraduate, and doctoral students and prominent faculties. This chapter aims to focus on developing the habits of professional growth with technical and scientific approaches. Also, to bring together the ignited minds and contribute to the computing community's scientific development through various activities such as workshop, webinars, and coding competition and many events. I am honored to welcome you all to this tech talk on merely fun with algorithms. It is our pleasure to invite our speaker, Professor Sajal Das, Professor and Daniel St. Clair Endowed Chair, Department of Computer Science, Missouri University of Science and Technology, USA. We are very grateful for this valuable time that we get to share with you. Now I invite Dr. Lavi Jain to introduce our speaker.
Hello everyone. I hope you can hear me. So, as you all know, we have Professor Sajal Das with us today, and he has been already introduced. And I hope you already know him because he also gave one talk last year. So, you also know that he's our adjunct faculty, and we are lucky that currently he's visiting us, and we are fortunate to hear him in person and have him here. So, thank you for visiting us, Professor Das. Over to you. Please.
I think if you can get the
speaker,
that would be good so that you can hear their question. Good afternoon, everyone. Are you able to hear me?
Yes, sir.
Good. We are trying to get the audio speaker set up so that the people in the audience over here also can hear you. All right. So first of all, thank you very much for being here online or in person late in the afternoon. And I appreciate IIT Jodhpur, the director and the computer science department, Dr. Richa Singh, Dr. Devashish Das, to invite me to campus. This is my second visit to this campus. So what I'm going to do, I thought this time instead of giving a pure research talk, let's give a very basic talk. It's almost like algorithm 101. But basic, but at the same time, I believe that you'll be learning something that you may not know, right? So it is very fundamental basic, but at the same time, I want it to be very interactive. So people who are on the audience, online or in person, I want you to interact as much as possible. My job is not to load you with information, but talk about something that we all should be learning and interacting. Okay? So the topic is merely fun with algorithms, because algorithm is bread and butter for computer science. You cannot live without it. You cannot be a better programmer unless you are a better algorithm designer, right? So because you know the famous equation, algorithm plus data structures equal programming. And there's a book that was written by Nicholas Witt in early 70s. He's the inventor of Pascal language. And when I was undergraduate students, that's the book we read. That was a textbook as a data structure book. The title of the book was Algorithm plus Data Structures Equal Programming. So what does it mean? If you want to be an efficient programmer, you want to write efficient code, it's not only important that your algorithm is very efficient, but your data structure is also very efficient, because data structure could be the bottleneck. Because, right? So that's the good part of it. And another incentive for learning, I'm talking about especially undergraduate students over here, that if you want to have any job interview with Google, you know their first interview is never on the coding or programming exercise. First interview is always on discrete math, data structures, algorithms. If you pass that first level of interview, Second interview will be testing on your coding skills, right? Because Google knows that if you are a good algorithm designer, if your fundamental concepts on discrete math, data structures, algorithms are good, you can always be a good programmer because it's a matter of codifying that to a particular syntax of a language, right? Then the third interview, of course, they usually bring to their campus and interact with. So there's a tremendous impetus and incentive to learn algorithms from the bottom of your heart. Okay, I'm just talking about all of us. So let's move on. So there's some warm-up, simple questions. I want everybody to interact as much as possible. Either you raise your hands or you just speak out. Okay? So first, a simple question is, how many of your students here raise your hands? And I thought that we are all students forever, including myself. Now the second question is, again, there's very generic question. Some of the things that we talked about the other day with the PhD students. It's very important that what motivates you. Is the motivation external or internal? Internal motivation, that means I have the urge of learning. External means I work for the grades. Or I want a job or something. So think about, you ask yourself, what is the motivating factor for you to learn something? And this aspect is for the courses, for the research, for anything that you do. Anything that you do, right? And the third question I have is, what is the difference between a student and a teacher? I want somebody to say that. What is the difference between a teacher and a student? Yes. You speak loudly so that people can hear. I do not know whether they can.
Students still learning, and teacher already learned for us. So the teacher have more knowledge than teacher.
But you see, the first bullet was, who are students? We all are students. We are still learning. We are ever learning students, right? So yeah, it's true that they may have more knowledge, right? So the context I'm bringing over here, and you'll see why I'm saying that, because today's student will be tomorrow's teacher if they want to be in academic profession, right? So there's a continuum, and that's my feedback control loop. So for example, let's say you are a student, you go through a higher learning and education institute like IIT Jodhpur, and through that process, a fraction of and there could be teacher not necessarily here, and then you train another set of students, right? Now, why is this important? Because the fundamental concept in the classroom is a mutual learning environment. It is not only one-sided dialogues or monologues from this side. That's the whole reason that we want this talk to be very interactive. We learn from each other, right? And you can see that this is a transfer function. You think that this yellow box or green box is an algorithm. If that algorithm does not have a very efficient outcome, that means you'll be producing weaker students, and there'll be faculty, they'll be producing even further weaker students. So there's a responsibility for all of us to make sure that this particular transfer function has a high gain. It's a feedback control loop, right? Now, having said that, this is a very quick overview of our campus, founded in 1870. It's a very STEM-focused campus like IIT, IISc. It's not a huge campus. It's about 8,000 students, mainly focused on science and engineering, just like the IITs. Very STEM-focused, science, technology, engineering, and math. And you see that those are the female students in our department. Now, what do I do? I'll just give one snapshot of it, and then I'll talk about the basics of algorithms and some fun stuff, right? So in our group, we have a lot of different things in the department. In our groups, we do networking, computing, and applications. Networking, computing, and emerging applications. You see that networking, different kinds of networking, different types of computing, and different types of applications. Could be smart environments, smart cities, cyber physical systems, all sorts of different things. Okay, but they are not really horizontal because they cut across. And of course, security, privacy, dependability is a common theme because you need from the device perspective. Devices give the data. Networking technology distributes the data. You need huge amount of computation power because big data analytics, machine learning, all sorts of stuff. Then you support services, applications, right? And of course, our research is not just scientific and technological, but also socio-technical, because When you talk about cyber-physical human systems, then humans are also involved. There are human dynamics. That means what kind of models? That could be game theory, utility maximization, socioeconomic theory, all sorts of different things come in the picture. Behavioral model, because security is not in isolation with the technology, because sometimes humans also are involved in the vulnerability and attacks scenarios. Most often, right? Question: what is their motive? What is their behavior? How do I incentivize them to be not an attacker, for example, right? But I am trained in algorithms and graph theory. Okay, so whatever we do, there should be an underlying algorithms. Some efficient solution, architecture, algorithms, protocols, modeling. So we do enough of mathematical modeling from algorithmic perspective or otherwise. And then, of course, also do hands-on validation. So real prototype building, experimentation, or simulation, depending on. So we do a combination of both, like algorithm design, problem solving, modeling, and proof of concept validation, and technology transfer, whatever we can. So essentially, we do from sensing to anything smart, smart living, which means whatever impacts our daily life, how do we improve it? Be it energy efficiency of the building, or activities monitoring, or health monitoring, or smart transportation in a congested city, air pollution control. This is the application domain. Okay? Now, one more slide I'll show, then I'll go into the algorithmic part. I have been very fortunate to collaborate with a lot of people in India, either the students who came to work with me, or I have my collaborators over here, including, as you see, as Dr. Pallavi Jain mentioned, that I have some affiliation with this institute, and I already have a very active collaboration with Dr. Debashish Das, and some others probably will emerge. That whole purpose of visiting over here. So you can see that different institutes are there. I don't want to read. And that's my passion, to work with students, with colleagues. Collaboration is fun. That's the whole premise of this talk, right? Now, when you talk about fun or merely fun with algorithms, what do I mean? And I'm actually using a quotation, and some of you may know the quotation comes from somebody. So I want you to think, whose quotation is this? And the question I'm asking people online or over here. So, pleasure has always probably been the main goal all along. So, getting joy out of doing things, right? But I hesitate to admit it because computer scientists want to maintain their image as hardworking individuals who deserve high salaries. Sooner or later, the society will realize that certain kinds of hard work are in fact admirable, even though they are more fun than just about anything else. And this comes from a Turing awardee computer scientist. Does anybody know whose quotation is this? This quotation comes from none other than Don Knuth. Have you heard of Don Knuth? Yes, Donald Knuth? Yes or no? No? People online, have you heard of Don Knuth's name? If not, I would suggest strongly that you do. It's not only that he is a Turing award, you got Turing award in 1974, but you actually recollect his contribution all the time. He is the one who standardized the big O notation, big omega notation, small omega. So he basically standardized in the 1960s how algorithms complexity should be represented, denoted. And then, of course, he has other contributions too. A lot of different contributions, like if you know string matching algorithm, pattern matching algorithm, the Knuth-Morris-Patterson algorithm, for example. Right? So different things there. But he was not only a computer scientist, he's a theoretical computer scientist. He has actually multifaceted talent. He was a music composer, computer music composer. Right? And not only that, you may not have actually seen this book, but I would strongly suggest take a look at those books that he has written. Some of these first 3 volumes of The Art of Computer Programming was written in early 1970s. When we were undergraduate students, early 80s, we read actually first 3 volumes. The 4th volume came out just a few years ago. These are the Bible. All of these books were written about 50 years ago. It has a different types of language syntax called mix, but the fundamental concepts. The first volume is on data structures. an algorithm. Second volume is semi-numerical algorithms. Third is sorting and searching. The whole book on sorting and searching, written in 1973. But so think about it. And you also know that he's the one who standardized the text formatting, TeX. And then Leslie Lamport put some macros, it became LaTeX. And also the concrete math is another book that you should read. It's a very strong book on discrete math, a little challenging, but it's a very classic book. Okay. Now, this is the thing that I'll point out over here. He coined this, the art of computer programming. So computer science has tremendous amounts of science, theory, everything, right? But it also has an aesthetic beauty and art around it. Right? So you see that what he says, computer programming is an art because, and he's a theoretical computer scientist, he's an applied mathematician by training. And he worked with the very first compiler that IBM produced, Fortran 4 compiler in 1960. Because programming is art, because it applies accumulated knowledge to the world, because it requires skill and ingenuity, and especially because it produces objects of beauty. So how can you get fun and joy and pleasure unless you see the beauty inside it? The computer science actually may look abstract, may look very dry and cut, but you should be able to find that art inside it. That's why actually you become a better programmer when that art is embedded in your code. That means I make it so beautiful that people understand, and also the code is very elegant. It's not a spaghetti code. So even though some of you may want to be a software engineer, computer programmer, but still do not neglect the theory and the algorithms, okay? So this talk is more pedagogical in that sense. A programmer who subconsciously views himself as an artist will enjoy what he does and will do it better. And I believe it's very strongly. Right? So it's again Don Knutz. Now let's come to the main part of the talk, which is again algorithm 101, but I want as much as introduction as possible. I don't see everybody right now who are online, but I hope that everybody can interact. Now you know different methods of strategies for algorithm design, right? Whether it is a deterministic or randomized, probabilistic, the different techniques that you know. But in my opinion, designing very elegant algorithms which is beautiful, simple. So simplicity is beauty. Simplicity is elegance. So how do you design a very simple algorithm, but you say, wow, there's an aha factor, wow factor, right? And that's the type of algorithm that brings you joy and fun. And that only can happen in your research or otherwise in class project when you understand that problem and you're very meticulous about it. How do you solve it in the best possible way? So that's the whole goal in computer science, the best possible way. But at the same time, don't make it very dry and cut, very simple and elegant. So designing elegant algorithm is fun. The more fun in analyzing them. Often it is not that easy, especially if you want to prove a bound, a lower bound, if it is there, or any other bound, approximation bounds, online complexity, whatever, right? And of course, the harder part is also proving the correctness sometimes. Right? So let us all get immersed in some of the very simple problems in an interactive way and feel the beauty. Just like though you pass by, you see a beautiful rose or a flower. It's, beautiful. I'm so happy and satisfied. You design a solution, and I'm talking about algorithm, but it could happen in any domain that you ponder into. Okay? So let's choose a very simple problem because most of these problems are very recreational and simple in nature. But I want to point out that there are ways to design these algorithms which should be very beautiful and simple. Right? So what is a knockout tournament? Bhumika?
Knockout, it's only one chance that you
Right. If you lose, you are knocked out. Right? It's not a league that I have so many chances or rounds. So knockout basically means table tennis, any football, any game, right? Or two players are playing, two teams are playing. You lose, you are out. That's a knockout tournament, a single chance, right? So let's say our input is n teams or n players, right? Whether between two teams or two players. So very simple question first to start with. What is the minimum number of games to be played to select the winner? Here winner means the best team or the best player. I have n players. I want to find a very simple question I'm asking to as a warm-up. I want answer either from online audience or from the room. What is the minimum number of games to be played to find the winner? Which is the best team? How many games? Hello? Anybody?
Assuming that each game has a winner and loser.
What is the answer?
If we assume that every game has a winner.
Did you hear what he's saying? Every game has a winner. Every game has a winner. Yeah, but I want to find the best, right? I have n teams.
Then
n minus 1.
How many?
N minus 1.
N minus 1. And that's the best that you could do, right? Okay. Fair enough. If I ask the question, how many additional games do I need to have to select the second best team?
Because whoever wins the game, the losing will be the second best.
No, that's a runner-up. Runner-up may not be the second best, right? You never say that they're the second best team or player. You say runner-up. That means they happen to be playing in the final. Yes?
One additional game. So n minus 1 plus 1, that is n.
N minus 1 plus?
1. So total comes out to n.
Why 1?
Because when the winner is taken away, then there are two teams competing for the second best.
Does everybody agree with that? So the question is, I already found the winner, which is the best. I want to find the second best.
Sir, the one team which lose at the end with the winner can be the second best team.
So who are the possible candidates? Who are the possible candidates for the second best?
I think it would be one more game to be played because once the winner has been selected, then we require one more game to play to come up the second best team.
Who are the candidates? It is one more game that is.
After the winner has been selected, then one more game is to be played for deciding the second best team.
Who are those? Is the runner-up? Another one is?
The second runner-up, you can say.
Why? So think about this way. The second best player of the team may be very unlucky. They got eliminated in the first round.
Additional n minus 2 games.
The winner who has played with all the people from starting can be the candidates for the second best.
Everybody or all the teams?
That winner who has played with all the candidates from starting.
Who is that? Which team played with all the candidates? It's not a league.
Winning team.
Sir.
So that means all the losers of the winner are the possible candidates, right?
Yes, sir. Yes, sir.
And how many of them are there? Is it clear, everybody, that all the losers of the winner are the possible candidates for the second best? Correct? And how many of them are there?
N by 2.
N minus? Why? It's a knockout tournament. Think about logically what is happening.
I think it would be 0 game because
Why 0?
The final will be played between the two only, and the winner is selected, then the second who loses will be the.
Is a runner-up, not the second best. Runner-up is not necessarily the second best. It could be.
I think, sir, because there cannot be any second best.
Why not?
Because it's a knockout tournament, so only one can be the best.
No, but if you think of, you eliminate the best, then whoever is the best among the rest would be the second best, right?
Sir, login.
Is it, you are almost there. Is it log n or log n minus 1?
Login minus 1.
Log n minus 1, right? Because think about your virtual binary tree that we constructed through the knockout tournament. Like two teams are playing. You have virtual binary tree, and that's the construction flow, algorithmic flow, right? And the root was the winner. If you eliminate that, say log n minus 1, right? So your log n minus 1 possible candidates. So how many more games do you need to play to find the second best? You already have the answer. Think about it. When you have n players,
the whole minus 1 again.
What is that?
Log n minus 2.
Log n minus 2, exactly. Because when you have n teams, you have n minus 1 games. Now you have log n minus 1 possible candidates, right? That means basically one candidate from each level of the binary tree. Because it's knockout tournament, that means at every level of the binary tree, which is a logical tree, the winner played only one game at every level. And he went all the way up to the root. That's why he's the winner, right? So you can see that that's why we always call runner-up. Because this is a very simple question, but very intriguing question, in my opinion, right? Now, if I ask the question, in computer science, we do the best case analysis, we also do worst case analysis. So let's say I want to find simultaneously the best team and the worst team. And I want to find the minimum number of games that needs to be played. Hello?
N into n minus 1. Like each team will be playing with every other player.
Yeah, so how many games?
N into n minus 1.
No, I'm not doing a league, right? It's a knockout tournament.
Yes, sir.
So I'm not playing with everybody else, right? So the premise is still knockout tournament. But I want to find simultaneously the best team and the worst team. Why n log n? Anyone? So I could do very brute force, right? Just I find the winner, which is n minus 1 games, and I eliminate the winner, and then I find the worst. So worst is just the reverse process, right? If I do, how many games do you need to play?
Is the answer 2n minus 2 for simultaneously best team and the worst?
2n minus 2 or 2n minus 3? Yeah, 2n minus 2 or 2n minus 3, whatever you call. But that's a very brute force. So basically, I find the winner and eliminate it, and then find the loser, right? But I'm not happy with this. So whoever is said 2n minus 2 or 2n minus 3, that's a solution, but I'm a computer scientist. I look for the best possible solution. I'm not happy with it. Can I do better? That means, can I play fewer games than 2n minus 2 or 2n minus 3? And I can still find both the winner and the best team and the worst team. And here actually, let's move forward. These are the things that are very good to work on the board, but we don't have the opportunity. So now let's go back again one more time to selecting the best team. So I'll give a divide and conquer simple paradigm that you know, and that will also be applicable to find both the best and the worst team.
अच्छा मैं मानी गई ये brute force समझाता मेरे को.
Hello?
हाँ.
Any comment? Or is somebody else is talking noise? So let's first think about very simple divide and conquer. Divide and conquer is same as the recursive algorithm, right? But this is the thing that n minus 1 comparison will come. Let's say I just divide into 2 subteams, right? N players, let's say n is a power of 2. Then recursively I play among n by two teams, I get winner. And from the second sub-team, a group, it's a group, I get another winner, right? To find the absolute best team, you basically play between. See, that's exactly what is happening in the binary tree, right? If you think about, I got left child of the root is one winner, right child of the root is another winner, you play with that, right? And if you do that, this is exactly n-1 games, right? And this is a recursive algorithm, so number of games. So here the time complexity I'm saying is proportional to the number of games, right? And I'm assuming n is power of 2 so that I can divide it every time. Okay. I want your help because this is an algorithm 101 course. I want you to, that's the way I designed the algorithm. I want to analyze it now. It's a recursive algorithm. That means my time complexity is proportional to the number of games that I play. How do I write the recursion or the recurrence relation? Any recursive algorithm has a recurrence relation that gives the complexity analysis, right? So if Tn is the number of games, that is broken into two sub-teams, can somebody help me to write the recurrence equation? Anyone? So Tn is equal to, I'm sure that you have taken algorithms course, undergraduate course, graduate course, everywhere. How do you write the recurrence relation?
2Tn by 2.
2Tn by 2, then y minus? So you see, Tn by 2 for the first group, Tn by 2 second group, 2Tn by 2 plus 1. I'm just going to very basic, but let's build on that. But when there are two teams, then of course one game is enough. That's the boundary condition. And you have done this thing, right? And if I analyze this, what will be the number of games that you need to, what will be Tn, the solution?
And log n.
Why log n? The log n steps. This is not log n because you said that how many games do you need to find the winner?
Earlier I said 2n minus 2, then 2n minus.
No, I'm talking about just the winner.
N minus 1.
N minus, that means this equation should give me n minus 1. It cannot be log n, it cannot be 2, n minus 2. So this equation is and you can do by many different ways, through recursion tree, through repeated substitution, right? If you just go through the steps by repeatedly substituting the same equation is recursion, right? I'll not show everything. So basically you'll get a GP series. And I go for k steps, which is log n number of steps, right? Which is the depth of the binary tree. And this is nothing but exactly n minus 1. Now, I showed this because I want to apply the same technique to find the best and the worst team. But in general, to find the winner, I don't have to go through this recursion, right? It's like finding the max of n integers. So finding the winner of n players is the same as finding the max of n integers. N minus 1 comparison. Each comparison is a game. You can see the same thing. Now, if I go to the same exercise now to find the best and the worst team, how should I do it? Now, here, of course, we already talked about it. The additional games that you need to play to find the best, second best, is log n minus 2 games. Because you're reusing the results that you already have. Because if you think about a tournament in your club, you don't play the game second, you already noted down in your logbook. And noting down is nothing but storing in the memory, and the logical is a binary tree. That means I'm reusing the partial results. I knew what happened in different knockout games, right? I'm reusing that, so that's why you have. So this reusing the partial result is a very powerful technique. We'll see that. So now I'm finding the best and worst by following the same mechanism. What should I do? I'm doing recursively. I have two subteams, n by 2 each. I'm finding best as well as the worst. Let's say from the first group, I have best one and worst one. From group 2, I have best 2 and worst 2. How do I find the winner? Between best 1 and best 2. And the worst would be The loser of the worst one and worst two. I'm just doing recursively. See, I showed the recursion in the last page slide so that I can actually apply the same technique. Now, if I want to find out now, okay, I'm finding simultaneously the best team and the worst team. How should I write the recursion now? Last time it was Tn is 2Tn by 2 plus 1. And what should be the equation here? Plus? Why 3? Plus? Why 3? Because only 2 games, right? Best is winner of best 1 and best 2. Plus 2. And again, if you have 2 teams, one game will tell who is the best and who is the worst. What will be the solution of this equation? All this difference is that you have an additive term 2 instead of 1. These are 2 games, right? What do you think will be the solution of this equation? If you follow the same technique, repeated substitution, recursion tree, whatever. N minus? N minus 1 to find the best. N minus 2 to find both. It's a recursion. Basically, you have to solve this recursion. And I'm assuming all of you are very much conversant of solving recurrence relations. So you see that even though I have only an additive term became 2 instead of 1.
3n by 2 minus 2.
Hello? How much?
3n by 2 minus 2.
2n?
3n by
3n?
2 by 2 minus 2.
Fantastic. If you just go through the exercise, 3n by 2 minus 2 is 1.5 times n. And which is much better than this, right? Because if I had done brute force, you find the winner, eliminate it, and find the worst, right? So you can see that a divide and conquer simple approach gave me a solution. Now you may say, oh, instead of 2n minus 3, I have 1.5n. Think about it. If I talk about shorting 130 crores of people's age in India, then your n is very large. So 2n versus 1.5n makes a lot of difference. Right? So question again is, and this is the best that you could do. So instead of 2n minus 3, I can do in 1.5 times n. Okay? But you see how this little trick by a simple divide and conquer, simple and elegant, but you see that the addition term that I had too, if I continue doing it, basically the equation changes a little bit. Okay? I want you to feel very comfortable in not only designing cool algorithms, but also analyzing it. Okay? Now you see that, so basically I also made use of the partial results, right? Because recursion does that. And you have a stack pointers to come back into the implementation, right? Now I'll apply the same technique to do something a little bit more involved now. Have you seen this problem? The multiplying 2 long bit integers? So long that I cannot hold in arithmetic logic unit in the register in the computer hardware. Because I may have 2000 bits by 2000 bits multiplication. Most often your architecture will support what? 32, 64, maybe 128 bits architecture. Okay? But you'll see that. So think about this first. And this is a question to everybody. Again, my job is not to talk too much things, but simple things, but let's see how do I do it. So if I give you 2 long n-bit integers, if you apply your elementary school, high school technique, what will be the complexity? 2 long n-bit integers. I can see decimal bits does not really matter much, right? If you just do the same thing, that bitwise multiplication first, then do the shift, and then after all the multiplication, you do the addition, carry forward the. What will be the complexity? 2 long n-bit integers I'm multiplying by my simple elementary school multiplication technique. n square. Order is n square, right? I can do, because you see, I need so many multiplications, n multiplications, dot products, right? And then some addition, some shifting and all, right? So it's n square complexity. But I'm not happy, I'm a computer scientist. Can you do better? And this is a question I'm asking before I show the solution. I'm asking, I am not happy. See, last time what we had, instead of 2n minus 3, I had 1.5 times n. A coefficient changed from 2 to 1.5. Now I am aspiring to change the exponent. Instead of n square, even a smaller complexity. And that will be very significant. So question is, can I multiply two long n bit integers faster? Even for decimal, I can do the same thing. The same technique will apply. Okay, let's see. So let's apply the divide and conquer again. Okay. So I'm taking this as a more recreational algorithmic learning at the end of the day, but work with me. Divide and conquer. Divide and conquer is a beautiful approach in general. X is so long. So both X and Y are n bit each. I'm assuming n is a power of 2 so that I can divide it equally. Right? So I have most significant n bit, n by 2 bits, A. B is another string of n by 2, is significant, right? So if that is the case, then X should be what? A times 2 to the power n by 2 plus B. B is a string, is not a single bit, right? And I can do the same thing for Y. Just follow me. And I want you to ask the question now. Now, if I do X times Y, I'm multiplying X and Y. If I do a simple algebra, what would that be? Only thing is that A and B and C and D are strings, binary strings, instead of single bit. Right? If I do that, it's a very simple algebra. Right? You'll have the 2 to the power n is very simple, right? Multiplying, because you just do shift n bit shifting to the left, right? 2 to the power n by 2 bit shifting to the left. Because once you do one bit shifting, is multiplication by 2. So this will be the case, right? Now this is a recursion. Divide and conquer leads a recursive algorithm, and that's the time complexity. Here the time complexity will be number of multiplications, addition, subtraction, but the number of multiplication is more expensive. Let's focus on that. Okay. So what will be the equation? Recurrence relation. I'm multiplying two n-bit integers, but Tn is multiplying two n-bit integers. If I write the recursion, I need somebody's help. Now multiplying two n-bit integers means have 4 multiplication of n by 2 integers. A is n by 2, C is n by 2, that's one multiplication. But this multiplication is not a single bit multiplication, 2 substring multiplication, recursively, right? Similarly, AB, both A and D are n by 2 each. BC the same, BD. I need your help to write the recurrence relation. I know some of you on the online are very good in responding. Please do respond. I don't see everybody. How should I write? The time complexity is the number of operations. Multiplication, addition, subtraction. How do I write Tn? Anyone? So this is trivial, right? If I have 2 single bits, if n is 1, that means I'm multiplying 2 single bits. I just need 1 multiplication, nothing else. What should Tn be? T of n is anybody there online? Anyone from here? Tn is? How many smaller multiplications are there? 1, 2, 3, 4. So is it fair to say that the 4 multiplication recursively of size n by 2, then you have some additions, This addition is on the bitwise addition, right? So that's why I put some constant times n, because addition operations is order of n. And if you solve it, what would be the solution? You can apply master theorem, or you can solve it the same way you have done the other two. What would be the solution? Anyone? So I want everybody to feel very comfortable. Maybe you go back tonight and brush up your algorithms as well as the analysis techniques. The same technique that you have applied, repeatedly you substitute. If you do that, you will get n squared. Your elementary school mathematical technique also multiplication says n squared. I went through a very rigorous process, and this process is not easy to explain to a elementary school student. I ended up with the same complexity n squared. Would anybody care with my recursive algorithm, divide and conquer algorithm? No, because they say, what did you do? My third grade student can also do the same thing and give you the result. But, again, as I said, divide and conquer is a technique. Remember what we did for the knockout tournament to find the second best team or the best team and the worst team? What did I do? I made use of
common sub problems where
partial results, right? So that means this 4, if you apply the master theorem or even if you solve exactly, this 4 is actually contributing to, there's a log 4 base 2 that is contributing to the exponent. That means the logic now is, if I can reduce the number of multiplications in the recursion from 4 to anything less, that means that will contribute less in the exponent. Fair enough? How do I do it? That means I need to reuse some partial results. And that's where the clever trick comes from. Okay, so reuse some of the multiplications that I have done. And you'll be amazed to see that these were part of the research in the past. But now it is, of course. Because multiplication is more expensive than addition and subtraction. Because addition and subtraction is linear time, but multiplication is quadratic time in n, right? So let's think about very simple algebra. A minus b times d minus c is how much? It's a simple algebra, right? Now you can see that if I can get ad plus bc, the term that I have in x multiply y, I'm reusing SC and BD. Let's say I already computed SC, I computed BD, and if I reuse them, then I need to do A minus B times D minus C plus SC plus BD, that will give me AD plus BC. So for 2 multiplications, I actually reduce that way. Now A minus B is also n by 2 size, right? So basically, if I AD plus BC, I can replace with respect to SC and BD. So the total number of multiplication is what? 1, 2, and BD, because SC and BD is already computed. Right? So I'm reusing SC and BD, and then just having one more. So that means I have 3 multiplications which are distinct. AD and BC, I already computed, so I don't have to multiply all the time, SC and BD. So if I now write the equation, what would be the equation? So 3, right? 3 multiplications of smaller size, and then I have a little bit more subtraction which was not there, but addition and subtraction are both linear time. That constant C or C prime will absorb that. Now if you solve it, so this was, as I said, is 4 to the power n is to the k. So 4 to the power k, that led to n squared. Now if you solve it, it will be 3 to the power k. So k is log n. So 3 to the power log n is how much? If you do the base and the transformation, how much is it? So 3 to the power k, where k is log n, base 2, will be in terms of n, how much would it be? n? Just loud? Log 3. So because it was n exponential log 4. And this is precisely the thing. How much is log 3? Less than 2 for sure, log 2 for how much is it? It's close to 1.59. So you can see that from n square I went to n square root of n. Significant. You see that what I'm saying, if I know the tricks, because I'm reusing the results, that's the only way I can do it better. So I did not need n square. So I went through a rigorous exercise of divide and conquer. If I do very naively, I do not beat a elementary school method. But if I do a little trick, which an elementary school kid may not know, but I substantially save the complexity for n squared to the 1.59. Any question from the online audience?
This algorithm is called Carrot-Soup algorithm.
What is the question?
I'm asking, is this the Carrot-Soup algorithm?
Yes. Not you don't have to go to Karatsuba, you go to Strasson's. Exactly. So Strasson's matrix multiplication, let's say you're multiplying two matrices A and B, both of size n by n by n by n. So here I had n-bit multiplication one-dimensional. Two matrices n by n, right? If you do the naive matrix multiplication, is n cubed complexity. Row, column, right? But the Strasson's multiplication is how much complexity? And 2.81 is log? Yes, but 2.81 comes from where? Log 7 base 2. See, log 8 base 2 will make it n cubed. And the Strasson's multiplication exactly does the same thing. Only thing is that instead of one dimension, it's dealing with two dimensions. So your number of equations is a little more involved, but it's basically reusing the partial. And you are right, that from Strasson's, basically Karatsuba's algorithm came later, further fine-tuning it, right? But you can see that from n cube, you can do 2.81 because instead of 8 sub-multiplications of sub-matrices, and you're doing 7. So log 7 base 2. So it's exactly the same philosophy. So see that, and that's also divide and conquer. So finding the best and the worst, matrix integer multiplication of long bits, matrix multiplication, same logic. Good, very good. So let's look at another interesting and simple problem. How much time do I have? Okay. So if you feel bored, let me know. My talk is very modular and you can stop. Right? But I want you to learn something, but do not neglect. You may think that, oh, I'll be a coder, I'll be a software engineer, programmer, why should I learn these things? But you can save lakhs and crores of rupees for your company. Because if you can reduce the complexity from n squared to n to the power 1.59, n cubed to 2.81, right? You see that? You make actually innovation. So let's take a very other simple problem, because these problems are very basic problems you all know. What is the towers of Hana problem? I want you to tell me, what is that problem? And that you learn from day one, maybe in high school too, in programming class. What is the towers of Hana problem?
So actually there were 3 clamps and there was some ring space.
Okay.
With the condition that the bigger ring is at the bottom,
right,
and the smaller ring is at the top.
Okay.
Now, with the help of the third clamp stand, what we have to do, we have to shift the entire rings to the third clamp stand, so that the sequence has to be the same. Like the condition has to be fulfilled. Like the bigger ring has to be like at the bottom, and the smaller has to be at the top.
Very good. Everybody's with him, right? You know this problem. That's not an issue. You'll see that basically that's it. There are 3 poles or pegs, right? And here is the example for 3. But I could have any number of disks. I could have n disks, right? But the thing is that the largest one at the bottom, next largest, and the smallest on the top. And your objective is, so basically here, when B and C are empty, one of them will be destination. You choose who will be a destination. Think about it. So A is the source. And choose one of them as destination. Who is your destination, B or C? Let's say go for C. That means you want to transfer all these disks to C following certain rules, right? What is the rule?
The rule is like the smaller ring can only place at the top of a bigger ring.
And what else?
And we cannot shift only one ring at a time.
That's exactly what I have written. Only one move at a time. And at no time, the larger one is sitting on top of a smaller one. So when C is your destination, B is your auxiliary storage, temporary storage. Because you need to manipulate the data. It's a data structure question, right? And of course, you know the solution. I don't have to tell you because this you have done it. The first recursion, all you have written, very simple, 3 lines, right? But what is the smallest number of moves that you need? The time compressively proportional to the number of moves. So the question is, I want to find the minimum number of moves to accomplish that goal. What is that? And let's assume I have n disks. Here it is 3. I got n disks. How many moves do you need? 2 to the n minus 1. Does everybody believe in? It's an exponential number, but that's the smallest. You cannot do better than that. See, suddenly I went from a polynomial term and exponential for a simple problem. I still use divide and conquer, right? That's the way you do it. So how do you solve it in divide and conquer method? Divide and conquer or recursion. So what is your methodology? Let's say I have n disks. How do you solve it? Because when you set 2 to the n minus 1, that means you have some algorithm in mind.
So we actually divided into 2 halves.
Is it 2 halves?
Like we are using B and C, so we are using both as a like one time we are going.
Right. But recursively, how do you partition the problem? Or how do you solve it? So you're using, in fact, A, B, C, all of them will be temporary storage at one point. You can see that, right?
Yes.
But question is, what is the recursion here? Anyone from the online audience? What is the recursion that you have? It's a very classic example of a recursion. And again, it's algorithm 101. So basically what you do, since I have to follow that sequencing or ordering, right? You move the top n minus 1 disk to one of them. And let's say in this case is B. If I can move top n minus 1 disk to B, your C destination is empty, and you have the only largest disk sitting on A. I move the largest over there. Right? Now A becomes the temporary storage, B becomes the source. And I have n minus 1 left. So that means recursively, first n minus 1 I move to the temporary, then the largest one goes to the destination, and from the temporary n minus 1, with the help of the source, original source, I transfer. That means the recursion is n minus 1 at a time, right? So if you do that, that's your equation. And you know that. But you see that my partition is not good. In the previous problem, I was dividing in halves. And the partition is extremely bad. Only one disk went to the destination. That's why this one is basically the largest one goes to the destination. But partition was so bad. And if you solve this recursion by the same method, you'll get exponential term. You can see that if I had 2t n by 2 plus 1, then it becomes n minus 1. That was the finding the winner. But if it becomes n minus 1 instead of n by 2 in the argument, then suddenly I get an exponential. Because my partition is so bad. And this is the best you can do. Okay? But let's see another interesting stuff over here. I can also solve this problem from a graph theory point of view, which we call towers of Hana graph. Have you heard of it, towers of Hana graph? Yes or no? Okay, so let's hear. So this is the part that we have already talked about, right? So towers of Hana graph, it's a very simple, interesting problem, and you'll see that I can solve the same problem, all the movements, in a graph theoretic sense. So let's define a graph like that. N disks. I can have k poles. So k is 3 over here. But you see how many disks are there? 1, 2, 3, 7 disks. Right? So I can generalize the problem. Towers of Hana problem. There are n disks, and I have k different. Now in this case, k is 3. And I'm giving a ternary representation when k is 3, 0, 1, 2. If it's k, then it will be KRD representation. Okay? So in this graph notation, in any graph, as you know, there is a set of vertices and set of edges. I'm saying towers of Hana graph with n disks, k poles, which is h and k. The set of vertices, I'll define the vertices. Okay? Because any graph that you define, you have to clearly define what is the set of vertices, what are the set of edges, right? So I'm saying vertices are all possible configurations, the disks on the pole. What is the configuration? At the beginning, I have all three in one. At any intermediate stage, they'll go somewhere. So configuration means how the poles are being occupied. So if all possible configuration of disks on the poles, how many such configurations are there when you have k poles and n disks? And in special case, k is 3 poles. I'm asking you the question, how many possible configurations are there when you have n disks and k poles? And you can see one pole can have everything or any combination. It's a question, permutation question, right? When you have k poles and n disks, think. See, I'm allowing the repetitions because when you have repetitions allowed, think about k is 3. How many possible configurations are there? It's not NCK because I'm allowing the repetition. That means here all the disks are in pole 0, others are empty. So I could have any combination, right? So that means how do I distribute the disks into the poles, right? Anyone from the online audience? What are the possible configurations? It's actually k to the power n because I can have all n disks in one or in any other way with the repetitions allowed, right? So k to the power n. And then the edges are defined as the legal moves. How is the legal move? That means one is at no time a larger one will be sitting on a smaller one. I'm defining a graph with all possible configurations as the vertices, and from one vertex to another vertex, a vertex is a configuration. If I have a legal move, that will lead to a different configuration, and that gives an edge. Okay? Makes sense? And you'll see that I'll show you the Tower of Hana graph can have n disks and 3 poles. And in that graph, if I do a traversal, I have precisely the Towers of Hana solution. I don't have to go for a recursion. Still, it will require 2 to the power n minus 1 if it is 3 poles, right? So what I need to do, I need to do a little representations just to make it. So I'm talking about ternary representation, 0, 1, 2, 3 poles, right? So largest disk, let's say I call that a n minus 1. Think of it as a binary ternary string, right? That means a0, a1 up to a n minus 1. Ternary string in n digits. Okay? So the largest one is the most significant bit you can think. Second largest one, size-wise, and the smallest one. Okay? So that's the way, basically it's a representation or encoding. Now this is the thing. If k is 3, that is I have the Towers of Hana graph which is hn minus n, hn3. Okay? And that's the graph. So that's precisely the hn3 graph. Okay, and I'll define exactly what it means. That means each node has a level. As I say, it's an n-bit ternary string. And how do I define that? Is what is the value of AI? The value could be 0, 1, or 2, but AI is equal to j if disk AI lies on pole j. I have k poles, I have n disks, right? If it so happens that the disks are label like A0, A1 up to AN minus 1. Right? If this AI lies on pole J, then I say that AI is J. That's the way I have labeled those nodes. Okay, now let's take an example. So let's say the one that I put the red mark 002, what does it mean? And that configuration is same as what I have. Two distance pole 0, no disk on pole 1, and the smallest disk on pole 2. Poles are 0, 1, 2, right? So that's what it means. The largest disk A2 and the medium disk AI. So if you think from this angle, A2 and A1, they are on pole 0, right? So that's their values are 0. That is the first two. These are 0, 0. Smallest disk, which is A2, sorry, A0. A0 is on pole 2. So that means that value will be 2. That's why 002. So that's the interpretation of the level of the. So I have the configurations, and each configuration has a ternary encoding. And a valid move, legal move gives an edge. You see, all possible edges are not there. I have so many nodes. In HM3, I have precisely 27 nodes, right? Right? But all possible edges are not there. Very few edges are there. And because each edge is a legal move. That means if I can go from one node to another node, that's a legal move. And that gives a configuration. Okay? Now, it so happens that your initial configuration is 0, 0, 0. And all the disks are on pole 0. If the last one, the pole 2 is your destination, then means you want a configuration 2 to 2. That's the configuration you're looking for, right? If I do that, that means if I, in this case, actually it shows on the left, so that's the path I should traverse. And that's a, right? If I pass, and that has 7 edges. Each edge is a legal move. So that means you can actually define what will be your configuration that you want to reach. But that's the smallest path from the root 0, 0, 0 to that node. So if my destination was, let's say, 201, if that's the configuration I want, then I have to traverse a different path, right? Now, this graph is undirected. Because I can go back and forth, but I should not do that because that will be more moves. But it's undirected graph. It's a connected graph. Because every time I'm making a legal move to go from one configuration to another configuration, right? So I'm defining a graph out of my towers of Hana problem. As I said, length of the shortest path is the solution. Because my configuration initially was 0, 0, 0, and my destination configuration, what I want, everything should be transferred to pole 2. 2 to 2, right? All the disks will be in 2. And also this graph, you know Hamiltonian graph? That means you can traverse each node exactly once and come back to the starting point. And these red marks are actually the Hamiltonian cycle. That means I have a Hamiltonian cycle. Like traveling salespersons do, right? You visit each and every city exactly once and come back to the starting point. Okay? It's all self-similar because you can see the pattern. I have a triangle and the same triangle repeats, only with different encoding. And you may have seen similar structure on some of the screensavers on your laptop or computer. The Mandelbrot set. Right? It's exactly the same thing. It's a recursive structure. A recursion comes because I have a recursive solution. But I did not go through recursion. I went through an encoding of a graph and I said, okay, length of the shortest path from one configuration to another configuration gives you the sequence of moves from that point to that point. And I can choose whatever way I want to. Right? If I wanted everybody to be on destination pole 1, then my configuration will be 1, 1, 1. Okay? Now one can also see that this has some relationship with the Pascal's triangle, if you know what it is. Now, I can actually go on in many different ways. But let us give a pause over here. If you have any questions or anything, if you want to know more, I have lots of different interesting problems, but I don't want to bore you in the late hour. Let me hear from you, because I hope that you learned something that you did not know. Any questions from the audience, online or in person? We have several people in person in the room, and we have a lot of people in the audience, in the online. Any questions? If you want to know more simple problems, I have a lot of interesting problems. If you say, no, I'm tired, let's have some discussions, I'm for that. So you choose what you want to do. No. Is there anybody online? Or everybody has left? Hello.
Transforming any particular program into a graphical form, like this type of going to the recursive side, we have told us that we can solve it in a graph format as well.
Right.
So is it like all the time feasible, or you can get a good solution as compared to like the brute force or the recursive way which we are adopting?
It's a very good question. So, if you ask me the question, I love graph theory. Graph theory is my first love. Okay, my wife is the second love. So, what I'm saying that yes, every problem has some kind of graphical representation. Only thing is that we have to define very carefully what is V and what is E. Defining V is simple. Sometimes defining E is not that simple. But if I can do it, it's very visual. Right? You see the solution visually. Recursion is very dubious, right? You don't even know what is happening. It's very simple, 3 lines code. But how the stack is being manipulated, how the pointers are returned, you have to be very careful. Otherwise, I'm sure that you have written recursive programs that never terminated. Right? But so point is that yes, most often it's possible, but we do not know exactly how to define the edges or the vertices, right? Number one. And in terms of analysis, and why is it possible? Because every recursion can also be unfolded into an iterative method, right? So that unfolding to iterative method means I'm actually avoiding the recursion, right? So in this case, how did I unfold? Because I defined a configuration as the possible state. It's a state machine, right? Who is occupied? Which disk is occupied on which pole? That means I'm talking the state of the system, right? And that state gives me the configuration, right? And I'm saying from one configuration to another configuration. That's my legal move. That means whatever is the definition of the towers of Hana problem, I translated that to an edge as a legal move in the graph. Right? So if I did not take any left, that is, I could have done in another way. I come back to 2 to 2. That means you are taking more moves than necessary. Your objective is to minimum number of moves. Yeah, so in general, most often it is possible, but how? That's part of the research sometimes. Sometimes that actually makes it very intricate. Okay, how do I define it? But there are very interesting set of problems. The graphs are beautiful because you can visualize it. You can draw it. That's why graphs are so beautiful. It's a very nice modeling tool. If you have a good understanding of the graph theory, you can actually get solutions which are beautiful. I have lots of problems actually. If you are interested, I can talk about it. Further problems using graphs. And the proofs become very simple rather than being cumbersome, because objective is to define very simple and beautiful solutions, algorithms, analysis as well. Is there anybody online or is everybody gone? Some people are there. Any questions? Any questions, anything that you want to hear? Or, because I don't want to bore you. I'm very passionate about it. If you ask me, I can go on and on. But at the same time, how much you can absorb? Or if you want to have more interactive discussions, let's do that.
Sir, I want to ask one topic. Which language is more useful if I do data structure algorithm?
The sound is not coming.
Is
Did you
that,
understand what he said?
is that possible?
Yes. Some of the speaker phone is
You can also write your question.
Okay.
Now please ask again. Some of the speaker phone is actually creating a little noise. Did you understand the question, Lokendra? Yeah, could you repeat one more time?
Sir, I asked which language is most preferable if I want to do data structure algorithm.
So what did he say?
He's saying that if we have to implement some certain algorithm, which language will be more preferable?
Okay, the language wise, it all depends on the type of problems, right? See, when I was undergraduate students, we did not have very sophisticated compilers or API. And we did in a very rigorous way. But nowadays, it all depends on. Sometimes Python is more valuable, sometimes C++, sometimes Java, sometimes R language. So it all depends on, right? There's no one size fits all solution depending on the problem. For example, if you have an AI problem, let's say you're talking about a knockout tournament versus tic-tac-toe game or something else, then you have one way to do it, right? So it all depends on. But in general, what happens, a language is a language, it's a syntax, right? Once I know the syntax, most important thing is the problem solving strategy, which is the algorithm. I know how to design an algorithm. I know how to manipulate the data structure. See, partial results are stored in the data structure. You don't see this graph, right? In the memory is a data structure. So once I know that, then translating that to, so I cannot actually give an answer. It depends on which problem you are dealing with and which you feel very comfortable. I do not focus too much on the language. If I know how to use one language very well, I know how to use that syntax. Learning the second language, third language is very easy because you mastered one language very well and you mastered the logic of solving the problem. So I do not mandate the students that they have to write in Python versus Java versus C++, whatever. I say, whatever is your favorite language, but do it beautifully, do it elegantly. I want your solution. And the solution should not be spaghetti, right? So language is, so do you get my point? I'm saying that whatever is your favorite language. Learning a language is not a difficulty. Most often we do not understand the logic behind it. How did I solve it? Is it the best way to solve it, right? So I would focus on that, but language we have to, because ultimately we have to code it and implement it, right? So whatever you feel comfortable, if you feel comfortable with more than one language, go for it. And in different classes, actually, you learn more than one language anyway. Other questions? Yes.
Basically, we go for the computational complexity. But we should go for the space because space is also becoming very much important.
Yeah, so computational complexity, you do it because most often in the classes you deal with toy problems. Toy problems are not very space demanding. But we talk about resource complexity. Resource could be time, could be your memory space. I can give you a big data problem where even terabytes of data, picobytes of data is not enough. Petabytes, not pico, petabytes, right? Petabytes is 10 to the 15. So it all depends on the problem size, right? So space could be important. If the problem is mobile computing, wireless computing, then your wireless bandwidth is important. Because I can do a lot of computation, but I don't have enough bandwidth to transmit the results. I'm doing a distributed computation, right? What else? Resource is time, space, memory, bandwidth, what else? Energy, because nowadays you have devices, IoT device, sensors, smartphones. Right? Energy is very important. So basically we talk about resource. Depending on the nature of the problem, depending on the technology that you are using, time. So if you see that I have enough memory, my problem does not require more space, then time is more important. My student is running some experiments on a high performance computing platform. And the size of the problem, 10 to the power 24, 10 to the power 25 data size is that large. In that case, you have to be very careful how much I can bring to the memory, how much I store in the secondary, how do I minimize the traffic from memory to secondary cache, right? So in that case, the space becomes an issue. When you talk about wireless networks, sensor networks, all sorts of different things, mobile computing, then bandwidth, energy. Nowadays, even in computer architecture, you talk about energy efficient architecture, energy efficient processors, GPUs and all, right? Because energy is an issue. So resource in general. So when you design a solution, you make them resource efficient. Whatever is your metric for the resource, time, space, bandwidth, energy, or anything else. So as a computer science, you have a social responsibility. You are not just a programmer. You are solvers of those problems, because other people, they are not in computers, they can do program, they can use your package. But you are the one who are designing it. And your solution should be the most beautiful, aesthetically beautiful, simple, elegant, and the best. And if you can do that, that's why Don Knuth talked about the art of computer programming. That means you have to have the artistic view that this is really beautiful. And once you enjoy the beauty and get the pleasure of designing algorithm, then you'll see that it is absolutely marvelous. You have to enjoy the beauty. And since it deals with the theory, so I talked about very simple ones, the algorithm 101. But once you are into it, then you can go for more and more randomized algorithms, probabilistic algorithms, approximation algorithms, approximation to NP hardware, all sorts of things will come because once you have that interest. So if you're not refreshed about algorithms design techniques or analysis of it, very simple type of analysis, just brush your background. Because this should be your asset. You put stamp as a computer scientist because of those things. Everything else will come. Okay, other questions? Anyone? Does not have to be. You can ask any question that you want. So just one second. In online audience, can you hear the question that is being asked from the room? Audience online, could you hear the question? Otherwise, I'll repeat.
No, sir, I will not hear.
You can hear or you cannot?
Cannot.
Can you speak loudly?
So there is a thin difference between distributed systems and decentralized systems. So
I will repeat the question. Please wait. Yeah.
What is the broader difference that we can define in between this distributed and decentralized?
So the question is, there are some solutions which is centralized solutions. Some solutions are distributed solutions. Sometimes you can have hybrid as well. Some portions are distributed, some portions centralized, right? So your question is?
Distributed and decentralized. What is the broader difference?
Decentralized and distributed is almost the same thing. Yeah. So it's almost the same thing. So if you think the terminology, one is centralized means you have a central entity which basically manages execution of the different parts of the code, right? So it's a single computer, single processor like that, right? Decentralized means it is not centralized. So basically, decentralized is part of distributed, but I could have partially distributed, fully. Fully distributed means all the processors, they are working in cohesion to solve the problem. And what is the goal? Goal is to do the speed up. For example, if you have 10 to the power 20 order data size, conceivably you cannot solve in reasonable time with single processor, no matter how far, even a supercomputer. Right? So most often you take help of distributed solution. That means different portions are computed differently in different parts of the network or processors. But the challenge is that most often the different parts are not independent. There's a dependency. That means I need to do back and forth message exchange. Oh, what is it? Think about it. I give a class project. If you solve by yourself, then you are a centralized solution. 3 of you do it together, it's a distributed. The bottleneck is you do some part, he does some part, she does some part. You have to exchange notes. And the slowest processor will be the bottleneck. But your objective is, instead of single person doing it in 3 months, I want to speed up with 3 people. That may not be 1 month, maybe 2 months, maybe 1.5 months, depending on how much dependency you have, right? So a fully distributed means I'm partitioning the workload into different parts, in different processes, different units, but the problem may not be independent. It's not like, oh, you solve this, you solve this, you solve this, and then I'm done. Then maybe in between I have to do a lot of back and forth, because your solution depends on her, vice versa. And that's the bottleneck, and that's the message complexity overhead. So there's no free lunch. The goal is to speed up by distributed or parallel computation. Sometimes we say parallel and distributed difference, because shared memory is parallel, distributed memory is fully distributed message passing. Your goal is to speed up, but at the same time you pay for the message complexity or other overhead, synchronization overhead. A shared memory, then you're doing synchronization, the critical sections that you know in architecture operating system, right? There's a critical section, synchronization. If it's purely message passing, then how much message I should spend? What is the size of the message? That is an overhead, right? So it's a trade-off. It's a communication computation trade-off, right? So there are many different approaches out there how to balance that, load balancing at runtime. At the beginning, there may be good balance, but at runtime, depending on the data, it could be skewed. Right? So decentralized in general is not centralized language-wise. Now it could be partially distributed, could be fully distributed.
There might be some kind of authority, centralized authority involved in it, and in the second case, there is no kind of central authority in that.
Yeah, that's exactly what distributed mean in layman's term, yes. Right? But I could also have a hybrid, because sometimes you may have different units where there is centralized, but then there is a fully distributed. Think about the government organization, this IIT administration. A lot of autonomy and distributed in different units, but there's still some central authority. So it's could be combination. So you could have fully centralized, fully distributed, somewhere in between. But if you're solving problems as either machine learning, data analytics, large computation, I would strongly suggest that go for distributed implementation, high performance implementation, because it could be through clusters, through GPUs, or whatever, high performance machines, because that itself requires ingenuity. Because there could be synchronization overhead which will kill you. Message complexity overhead. Sometimes it will not give the correct result because they are not, these processors are not talking to each other in the right way. You are getting completely absurd result. That itself is very instructive to learn. So either simulation or actual experimentation, always it's a good idea. Because if you want to scale up, that's the only way. Because you want to solve larger scale problem, not a toy problem. So when you say time complexity, because most often in the classroom, you have a toy problem. Speak loudly so that others can hear. You're typing this so that everybody can see. Okay.
So one more question that I want to ask is, we are moving also towards the quantum computing.
There's a reverberation going on because you're talking as
we are slowly moving towards the quantum computing. That's going to be a reality. So in that case, these things that we have already have in this data structure and all these algorithms, will it change or they will work as it is in this computing environment, quantum computing environment?
So let me repeat the question if they have not heard it. So Lokendra is asking that we are moving towards quantum computing. Will that change the algorithm design paradigm or the solution methods or whatever, right? Now, two things. One is that we have quantum computation models, but quantum computers are not prevalent yet. Still a model. You don't have a quantum computer that you can touch tomorrow and implement, right? But you always start with that. You have the concepts, you have the model, then you see what is feasible, what is not feasible, right? So right now, quantum computers are not there. Some prototypes or some experimental test bed has been developed. Yes, so there are many. So basically, you deal with what we call quantum bits or qubits, right? So there's certain operations that you can do, which in the regular arithmetic logic unit with electronic circuit takes longer time, or it becomes very cumbersome. So quantum computation sometimes actually gives you an edge over there, right? But then, of course, there are other things that there is a quantum tunneling effect. There's lots of quantum principles come in the picture. That's why quantum computer has not been built in that sense. Although IBM, NASA, everybody is trying hard. They have some small stuff, but it is not widely, because you have to, first of all, to do quantum computing, you need the cooling, right? Superconductive materials. And why cooling? Because if you think at the fundamental level, the computation, everything is going into bits, right? At the machine code level. Bits means you have some digital circuits where you're doing flip-flopping, 0, 1, 0, 1, right? The faster computation means you're changing frequently these bits. And the frequency change in the quantum domain would mean the electrons are transitioning from one state to another state very fast. That's how you generate the heat. So one is thermal. So thermal, the frequency, if you move back and forth very fast, that basically heats up. That's the thermal part, right? Then in the quantum principle wise, in the quantum physics, that also can create, so thermal noise or thermal, it can also create a quantum noise, because the quantum levels are there. And if they are not switched properly, you get a quantum error, quantum noise, right? So multiple reasons are there. Since early 80s, so quantum computing is there, but at the same time, there are limitations in quantum computation as well. So, but it is widely believed, and which is true, that if you go through quantum computing techniques, so many problems which we think are hard problem, computational hard problem, I can do much simpler, right? But unless we have the machines yet, but no matter what you do, see, today's handset and laptop is powerful, more powerful than the supercomputer of the 80s and 90s, right? So supercomputer is very powerful now. So even if you get quantum computer, your problem scale still may increase significantly, that you can saturate. So technology is advancing, your problem size is also advancing. Larger problem size, more computation, machine learning, this thing, that thing, right? So that means your computation need is also much higher. The data size is much higher. That's why people talk about the Moore's law. You probably know that. The Moore's law gives the von Neumann architecture progression, that there's a limitation that we are getting, because speed is doubling almost 18 months, 12 months. Bandwidth the same way, memory the same way. But the battery technology is not advancing that way. So now we say Moore's law has a bottleneck. That means in the silicon level, even at the quantum level, there's a limitation how far we can go. There's a physical bottleneck, right? Physical science will come in the picture. From thermodynamics, from quantum principle, from relativity theory. And there has been a lot of study in quantum computing. What are the limitations? And those physical principles we cannot bypass, right? So at the end of the day, that's why people talk about beyond Moore's law. So quantum principle is one way, but that does not mean it to be the ultimate solution, because there will be some other limitations too, right? The same way you see in physical sciences. One model is you get a new theory, but the model also has a limitation. But yeah, keep an open mind, right? Don't thin out too much, but at the same time, don't be very narrowly focused. It's a good balance of breadth and depth is very important. So you understand what it means. You may not be working in everything, but don't use, my suggestion, don't use the buzzword or the jargons unnecessarily. If any word comes up out of your mouth, you should be able to defend it. I mean, what is that? If you say, oh, I'm doing deep learning. If somebody asks, what is deep learning? You should be able to clearly say that. Then if you just keep it very wishy-washy, that means you are just using the buzzword. So make sure anything that you don't have to force feed anything. Just because everything is working on certain direction with the hype does not mean anything to you. You solve fundamental problems. And if that problem requires a certain way to do it, that's fine. If not, still you have a value. And most often, I think we get carried away with the hype. And hype does not stay long. Sooner or later, it will be found out that you are very shallow. So anything that you say, just understand what it means. Even as a simple word in English, what does it mean? The question is decentralized. And which is not centralized, that is decentralized. Right? I could have fully distributed, I could have partial distribution. And so go into the very basic things, fundamental things, everything will be crystal clear. Most often we lose sight because we're talking many things, but we don't know what it means. And this should be true for the classroom exercise, for research and everything that you do. Build that as a habit. Is there anybody else online? Any other questions? So thank you very much. It's a pleasure to speak to you. Right? Are there any people who are? Is there any other question? Okay. Okay. Good. I see there are a lot of students are still there, but if anybody has any question, feel free to ask.
Thank you all for attending this session. Now we are closing the session. Thank you, sir, for this grateful and informative session.
Thank you very much. It's really a pleasure. I always love to interact with the students.